Normally, when you look around at your environment, both your eyes send information to the brain, then compiles two images into a single one. Now, it's this combination of two different two-dimensional images that your brain can then interpret into a three-dimensional image, giving you the depth perception. However, if you close one eye, look at an object like your finger fairly close to your face, then change the eye that is open, the finger appears to move relative to the background. The closer your finger is to your face, the more it appears to move. This phenomenon is called parallax and can be a fairly important principle in understanding the world around us. Of course, in the finger example, the finger isn't moving. Instead, what is happening is the line of sight from one eye is different to the other eye. As the eyes are in a slightly different position in your face, so the background behind the finger is different from each line of sight. So the brain interprets the difference as if your finger is sliding from side to side against a more distant background. And video games and other special effects use this parallax effect to give you depth of field to the images. Those images which are supposed to be close to the viewer will move quickly from side to side, whereas those that are more distant will move only very slowly. This change can also be the same when you're looking out of the window of a car or a train, where the distant objects seem to move past fairly slowly, as those close up zip by very rapidly across your field of view. This apparent change in position when viewed from two different points can be used to find out where things are, especially if the location is difficult to reach directly, using a form of triangulation. This could be for objects like hills really comes into its own when measuring the distance of stars. For a fairly long time, scientists thought that the stars were quite far away. But exactly how far away are they? And are some of them much further away than others? Well, by using the parallax effect, they could try to find out. Of course, just by measuring the apparent change in position of even a close star against a background of more distant ones, just by measuring from two different locations on the surface of the Earth, isn't really going to work, because the relatively small differences from one part of the Earth to another compared to the huge distances to the stars. However, the Earth doesn't remain exactly in the same place as it orbits the Sun. It also changes position, so at opposite times of the year, the orbital position of the Earth resemble the left and right eyes when looking at the finger. So you can measure the apparent change in position of the star from Earth by taking two measurements 6 months apart. You can create an isosceles triangle from the positions. 2 points on the Earth give you the base of the triangle, and from there you can get to the point of the triangle, which will be the star. Since we knew the distance that the Earth is from the Sun, we work out the length of the base of the triangle. And also, the apparent movement of the star, we can know the angle at the point of the triangle. So then some fairly simple maths to work out the length of the long sides of the triangle, which gives us the distance to the stars. Although this method has been surpassed by other methods, parallax gave us the first glimpse of the sheer scale and size of the universe.